Hello and welcome to the official week 5 video number 1 for assembly language csc314. Alright, so what we're going to do is dive more into basic syntax, specifically mainly looking at indirect addressing. If I pop over here, so we're kind of going through these notes in the outline. We've pretty much looked at numerous examples now of using registers and immediate operands. What we're going to look at now are what we call indirect operands, which are basically addresses or pointers. So hopefully that concept is reasonably familiar already from C programming. And so we're going to be looking at how those work, in what the syntax for those in assembly language is, and we'll actually then be able to see in the debugger, we'll actually see, how these things interact with memory. So hopefully that'll make it very concrete what these different addressing modes for indirect parameters or indirect operands actually mean. We'll also take a look at operand size. Everything we've done so far has been 32-bit, and that's simply implied because we've been doing everything with the 32-bit registers. So when we come over to our... Oops, I forgot to boot it up before I started running the video. Let's boot up our virtual machine and take a look at our code that we were working with. But every instruction example we've seen so far simply involved a 32-bit register, which implicitly makes the instruction a 32-bit instruction. So it interprets, if you give it an integer immediate operand, it's going to assume you want a 32-bit operand there. If you give it if you use smaller registers there than like the 16-bit registers, like AX instead of EAX or BX instead of EBX, when you use those registers, that makes the instruction a 16-bit instruction, and it implies that the size of chunks of things you move from memory and so forth will be 16 bits. Now, there are situations where you don't use registers directly in your commands, and then you need keywords to tell the assembler what actual size chunk of data you work with. You have more options than what I've listed here, but these are certainly the most common, and in a 32-bit architecture, it's certainly these three are the most common. You can bump some things up to 64-bit operations that will use two 32-bit registers in a kind of a combined way. We may get to that eventually. But for the most part, we're going to be looking at these three sizes here. 1 byte, 2 byte, or 4 byte are what we need to work with. So let's see if we've got our machine up. Yes, we do. And okay, so here's our program that we've been working with. And let me slide that down a little bit. And this is in the debugger, just where we left off last time. One thing I think I forgot to directly point out when we did that last step, when we added 1 to FFFFFF, I didn't expressly point out that in EDX we ended up with a 0. I mean, I had discussed it, so you knew what to look for. Hopefully you paid attention, or you were doing it yourself and you looked. But just to call attention to that, when we did that last step in the last video, adding 1 to FFFFFF, we did end up with a result of 0. And in fact, my machine state has been saved since I finished that video, so we're right at exact. As far as this virtual machine is concerned, no time has passed since I finished that last video. And right now, the instruction is still waiting to do the next instruction, which is the first of these 3 instructions that does the exit routine right here. But looking at all these other instructions we have up here, take any of them for example, we have a register EBX or a register EAX. It's the choice of register that makes these constants be 32-bit constants. Since I'm using a 32-bit register there, it's going to take that 100 and decide that that's going to be a 32-bit number, which is why when we look at the instructions in memory, okay, starting from start, that's why this first instruction is 5 bytes long, because the opcode is only 1 byte, and then that number 100 is being represented as a 32-bit number in memory. And so if we go back to looking at it as bytes, oops, why didn't that? Let's do bytes, hexadecimal bytes. There we go. So we have B8 64000000. So these 4 bytes from here to here, those 4 bytes represent that number 100. Okay, decimal 100, hexadecimal 64. Yeah, so that is using 4 bytes to represent that number because we specified a 32-bit register in the instruction, so the instruction is a 32-bit instruction. If we changed that to move to AX, then we would end up with only using 2 bytes to represent that number 100 instead of 32 bytes, or I'm sorry, 4 bytes, 32 bits. So we'd either use 16 bits or 32 bits to represent that number 100, and it all depends on which register. Are we using the EAX register or are we using the AX register? Of course, keep in mind that the AX register is just the smaller half of the EAX register. It just lets you name that half of the register and work with it as if it's kind of its own thing. But just remember, if you change AX, you are changing EAX. You're changing the 16 bits out of EAX. So keep that in mind. So that's where size comes in. We'll take a look at a few examples there. We'll mess with our program here. In fact, let me just click Run here to make this program finish. And let's exit KDebug and bring up our editor. And first thing, let's delete that blank line. Remember, we want when we're looking at this in the debugger, we want the code stripped down to the minimum. For some reason, it doesn't seem like the labels cause a problem, but blank lines seem to throw off figuring out what line to point to for the next instruction. So let's actually do some size things. So let's move EAX, comma, and I want to do this in hexadecimal. And the reason I want to do in hexadecimal is so we can actually see the bytes. Okay, so let's do something kind of funky. Let's do 1, 2, 3, 4, 5, 6, 7, 8. All right. And now I'm going to do another move. There's no reason to do this other than example. OX. Now here I'm going to, oh wait, no, I don't want to do an EX. I'm going to do an AX. I'll capitalize it just to emphasize it. The NASM syntax does not care whether you use upper or lowercase for these register names. I think it'll even let you mix them, and it doesn't care. Yeah. And now here, okay, this is just 16 bits. So 16 bits basically corresponds to these 4 digits of the hexadecimal number. And so I'm actually going to line it up just so they line up. And here, let's do FF00. Okay, so that's 1111111100000000 in binary. And let's just look at what happens there to the EAX register, just so it's very clear what's going on with these half register things. So I'm just going to save that. Let's rebuild, rerun, bring it up in KDBT. First, let me, okay, arrow up. There's the rebuild. There's the relink, and there's the KDebug command. So far so good. There's my new instructions, and oops, I put in blank lines, so it might get screwed up on the pointer. I forgot to leave it stripped, but I think we'll be okay. So let's actually just put the breakpoint here. Well, we'll leave the starting breakpoint. So let's fire it up. Because first thing I want to do is just look at the instructions in memory. So if we've got the memory view up here, so let's bring it to instructions, and we see that at start plus 27, we have the jump, then we have the EAX, let's see, here's the FF00, and there's the 1, 2, 3, 4, 5, 6, 7, 8. So this is what we're interested in. We're at continue plus 3, but we could also do that as start plus something, but I guess we can, let's actually put underscore continue in here as the starting address of the memory we want to look at. That way we can see it clearly. And now the first thing you'll notice is we go from continue plus 3, okay, here, and then continue plus 8, and then the exit is, oh shoot, it's going to give us exit. It's not showing. So let's go look at it as bytes. That may be easier. What we do know is that this position is at continue plus 8, and bytes, hexadecimal bytes. There we go. So there is that, and so it's nice that we have continue plus 8 right here on the side. So this byte right here, going like this, those are the bytes that we are looking at for this instruction. And actually, this doesn't look right. 1, 2. That's an instruction which should have 1, 2, 3, 4, 5, 6, 7, 8. And then we have there's the FF00. So it looks like what we ended up here is a 2-byte opcode. Actually, that makes sense. When you're going to these different size registers, you may not have the simple 1-byte opcodes anymore. So it's actually the instruction here is requiring 2 bytes. So this 66, hexadecimal 66 B8, these 2 bytes right here, those 2 bytes combined represent the instruction of copying this number into this register. Okay, and then the number itself is just 2 more bytes. So because we're only using a 16-bit register, it's going to take this constant and interpret that as a 16-bit constant, and it's only going to use 2 bytes in memory to represent that number. Whereas up here, because we're using a 4-byte register, it's going to take this number and interpret it as, where is that number? So that number is the last 4 bytes here. And again, little endian, so the 1, 2 is the largest byte, is the highest digits out of the hexadecimal number we're representing, but they're the last byte. So we have 1, 2, 3, 4, 5, 6, 7, 8. That's all because of little endian. Again, if we change our thing to words, then we see each thing here is 4-byte word, and there we see it interpreted as 1, 2, 3, 4, 5, 6, 7, 8 as hexadecimal that way. So so we see the 4-byte interpretation of this constant, but we see a 2-byte interpretation of that constant. And it has nothing to do with the fact that I made this constant small. If I had EAX here, then this would have been padded out with 2 additional 0 bytes, okay? Just like we see up here. These are small numbers. You don't need 8 hexadecimal digits to represent something that only needs 2 hexadecimal digits. But when we look at those, we can actually click this drop down and see our other things. So when we look at this first instruction and see how that number gets represented as bytes, we see the B8 for the instruction, and then we see the 64, and then 3 more bytes of zeros, so it's padding zeros to make a full 4-byte number of just hexadecimal 64. So again, these are leading zeros because of little endian. These zeros are higher value digits from the hexadecimal number. These are the lowest value digits, but they're the only things that have something in them. So this is just padding leading zeros in front of that to make a 4-byte or a 32-bit number. Okay, if we look at, we can actually find the OXFF, OXOO. So here, OX66B800FF. So right here where my cursor is right now, that is the instruction on line 18. So this instruction here, that's an interesting thing. If you click these little plus signs, I hadn't shown you this yet, but if you click these little plus signs on the side, it shows you the address of that instruction, and it reinterprets the instruction for you. Let's see if we can let's see, I don't have any in here. That'll be more interesting when we actually get to the indirect stuff. So so at any rate, that gives you an idea of the implied size instruction. So your choice of register determines the size of any other numbers involved, and you always have to use the same size thing. When you use constants, like here, if I tried to use a register that was too small for this constant, I think the assembler should give us an error message if we try that. But if you have a small number in a big register, it'll just pad out the extra zeros necessary to make a 16 or a 32-bit number. Okay, but at any rate, yeah, so that's something, a nice little feature of KDebug. It'll actually, you can just expand any single instruction here, and if there is anything to show you, it will show you. So those don't really have anything to expand, but here it's showing us that the address of this move instruction is this address right here. So even if you didn't have start or something to look at, if I wanted to see that instruction, I could just type this in directly. In fact, I might even be able to copy and paste it. Will it let me do that? Nope, wants to give me the step possibilities. But you can type OX804808E in here. And it just starts showing you the memory starting right at that point. So just different ways you can kind of look around in memory here. And again, anything you've put in there, you now have remembered in this drop down. We can go back to start and so forth. Okay, so so that is at least an introduction to operand size. We'll come back to that. Now I want to actually get into directly into the indirect operands and how they work. So we're looking at this right now, and we're going to take a look at how that works. So let's go and edit our file again and throw in some indirect operands. So what we've seen here, all of these instructions use immediate operands, and just copy that value from memory where it is immediately after the instruction into the register we want it to go to. What if you wanted to take something from a register, like we calculate EAX plus EBX? What if I wanted to store that into memory somewhere, right? Then I have to have some way of telling it that that's a destination I want something to go, right? So I could here do a move EAX. Oops, nope, that's the destination. I want the destination here. So I want a destination here. Let me just write the word destination and we'll figure out how to do that. So what I want to do is take that result that's in EAX and I want to put it in a destination out in memory. Well, first of all, I need a destination to put it. And so now this is where our other sections. We have the data.data section here, and that lets us define addresses for areas of memory that will be initialized with data. And then there's also a section called .bss. You may pick up in the reading where that where the .bss comes from, but really the names of these sections, except for the .data kind of makes sense, but the names of these sections don't really make much sense in the modern world. They made sense to the people that came up with these names originally. But here, let's say, what do I want to? Well, let's stick with the .data section since that's what I've already shown you. The .data, you reserve areas of memory and you initialize those memories. What we have already seen was setting up some text data. Let's do some numeric data. So I'm just going to define some constants like x and, or not constants, but actually I'm sort of defining variables, but x is really just an address to a location in memory. And then I'm going to say dw. Before you saw me do db. Now I'm doing dw. And then I'm going to give it a number to put in there. Let's say, I don't know, let's do 42. No, actually, let's do 42 decimal. Okay. And then I'm going to do y and dw. And okay, so 42 in decimal. Let's put the same number in y, but we'll do it using hexadecimal notation here. So I'm going to say ox. Let's see, we went 32, so that's 2 times 16 plus 10, so that's an a, ox2a. All right, put a 42. Well, let's say it this way. This defines x as address of first byte of a word at the beginning of the .data section, okay, in memory. So that's what x will ultimately be is the address of the first byte of the 4 bytes of this. So what makes it a word is the W there, okay? And here now we're defining y as address of first byte of a word. And I'll be specific, a 4-byte double word. Oops. That's something that in different contexts, word means different things. In our context, word means 2 bytes. We want DD, actually. Apologies there to throw you off. DD and DD. We want 4-byte words right now. Maybe we'll define some 2-byte words as well. So DD stands for data. The first D stands for data. The second D stands for double word. Okay? So this is defining x as address of the first byte of a 4-byte double word that is going to be found at the beginning of the .data section of memory. Y is now the address of the first byte of another word immediately after the previous word. So what do you suppose that means y will actually be numerically? Y will be x plus 5 or 4. Okay, so x is pointing to a 4-byte word. Then this new word. Whoops, where's my a there? Lost my a. Then this new word will be stored in the next 4 bytes, just because we list them in sequence. So this is going to be 4 bytes out of memory, and this is going to be the next 4 bytes out of memory, starting wherever the .data section starts in memory. It's just going to start reserving 4 bytes and 4 bytes. It's going to define x to be the address of the first 4 bytes, y will be the address of the second 4 bytes, and so forth. Okay. And let's see, this is probably enough to work with for now. What else? I wanted to say something else. Oh, the other thing is that we're actually going to store numbers into these things. Okay. So generally, what we think of as the .data section is traditionally for initialized data. You know, text strings for messages, numeric constants, and so forth. Now, it is read-write. You can change the values here, but there's kind of a traditional tendency to, this is where you kind of define constants for your programs, so you don't necessarily want to actually change the values of x and y, but you can. There's nothing that's stopping you. So we could actually, we'll look at instructions that can modify these, but more often you use .bss for variables, reserving memory, typically uninitialized, for variables. Now, like I say, there's not really a hard and fast rule. You could use the .data section for all of this. There's not a compelling reason why you have to use both, but just so you're kind of aware of the traditional usages of these things. And you could use x and y as variables and have your program modify the values that were stored at those locations in memory. And this way you're just initializing them. And so generally speaking, it's these D commands that reserve space and initialize. All right. And yeah, so let's see, do we actually want to look at .b? No, I don't want to throw too much at you at once. So let's actually use x and y here and learn about indirect addressing with the registers. Okay. So let's go ahead and save this. Well, actually, let's now have some instructions that use x and y. So here, again, we just had immediate operands going into EAX, AX there. But what if we want to take this result of doing this sum and send that to a destination, okay? And actually, let's go ahead and reserve one more space for that. So I'm going to call a label result, do another DD, and we'll just initialize it to 0, and we'll actually use this one for a variable. So each of these is, reserving an address of a 4-byte. So the address result will be y plus 4 or x plus 8 here. And I might as well flesh out this comment here. The address y will be x plus 4. Okay. So now we have an address result, and let's let that be where we store the result of EAX. So now you might want to say, use it like a variable, and just say result here. This will not work. And the reason is that result is really just a number. All these things, x is not 42. X is the address of where this 42 is stored. Okay. Y is not 42 or hexadecimal 2a. Y is the address of where this is stored. Result is not 0. Result is the address of where that 0 is stored. So that address is going to be some number, 4,576,298, whatever it is. Okay. You can't store a number in a number. You have to store a number in a place. All right. And saying result here is just a number, it's not a place. If we want to talk about the place at that address, we have to put square brackets around it. That will work. So now I have to take out this comment that says it won't work. So this says take the result in EAX, or take whatever's stored in EAX and copy it out into the memory location pointed to by result. And specifically, we're copying 4 bytes. So the initial byte will be the address pointed to by result, and then the next 3 bytes will also be filled in by the bytes from EAX. And the little endian kind of conversion is handled for you there. So this actually copies the number in EAX to the memory location addressed by result. Okay, and so we'll take a look at that. And let's go ahead and do a few more things down here towards the end. And let me strip out this blank line. What if I wanted to copy what was in X into a register? Let's say I want to move into EBX what's stored at X. Well, I can't just say X here, all right? In fact, I'm going to leave that there. This copies the address X, okay, into EBX. This is quite often a useful thing to do, but it means something entirely different from this. Move EBX. Now I'm going to use ECX. This. All right. So this copies the 4 bytes starting at address X from memory into ECX. Okay. And let's do something interesting here. Now I'm going to take this EBX and I'm going to add 4 to it. So let's do an add EBX 4 adds 4 to the number in EBX, which, recall, is the address X. Okay. And now I'm going to do one more thing. I'm going to let's just do another move right now. I'm going to move into, let's use EDX, since we haven't used that one yet in this series of examples. I'm going to move EDX, and what I want to do is get whatever I'm going to interpret EBX, what's the number in EBX, as an address, and get the memory that it points to. Remember, I started EBX at this address. I added 4 to it here. What does that mean? That means EBX should be pointing to Y. And you know what? I'm going to put a different number in Y just because just so I have 2 different things and it's very clear when we test this in the debugger what's going on. So so I'm going to do that, and so I'm going to move from what EBX is pointing to. So this copies 4 bytes from memory pointed to I'm going to say at address EBX, okay, so at the address currently in EBX, we can think of that as pointed to by EBX to register EDX, okay? So I think this is enough to start sorting out how this works, how these different kinds of indirect addressing work. And yeah, so we've seen using an address as a destination. We've seen using as a source in different ways, and here we're seeing using the address in a register rather than some address that is constant. The one thing here is that X, that's just going to be a constant. So the assembler is going to put your program together. Actually, it's probably the linker is what's ultimately going to figure out the numerical value of X. But once that's set, that's just going to be a constant in your assembly language program. But sometimes you want to work with arrays and you want to have look at memory at different addresses, and there's no constant to refer to what you want to look at, so you actually have to have do calculations in registers or something to get a new address and use that to refer to a location in memory. So that's what we're actually doing with this right here, and it's simply because we know that y is the same as x plus 4 and that result is the same as x plus 8, that we can figure out that the value of this EBX here, because we put x into EBX, added 4 to it, that means what we have here when we do this instruction should be the same as the address y. So that's the explanation. So now let's actually just see this in action. Let's save, rebuild, and rerun. Rebuild, relink, bring it back up into KDebug, and here we are. So I'm going to clear breakpoints here, and let's just go ahead and set the breakpoint at start and make sure we can see our registers. So we'll hit run and have it be ready to do the first instruction. We can see what's in the registers, see what's in memory. So before we actually go on, let's actually do the instructions interpretation here, because the one nice thing here is it's going to turn all these x's and y's and so forth into their actual numbers. Remember I said over here in the program, things like exit, continue, whoops, exit, continue, start, x, y, and result. These things are all just ultimately going to be the linker, the assembler and or the linker are going to figure out actual numerical values for these things, because they're just going to be constant addresses for things in memory. And sure enough, if we look here and we find some of these instructions, we have let's see. I want to make sure we're looking at what I want to look at. So our first one was move EBX. So let's find a move EBX in here. There it is. So right there, that tells us what the value of x is actually going to be. It's going to be 80490DO, which should also be the same as the first byte of data, of the data section. But if I put x here as our starting index, whoops. In this case, it's wanting an ampersand in front of it. For some reason, it doesn't. If it's a label like this, it's happy. But when it's defined the other way, it wants an ampersand in front of that. But once you do that, that makes it the address. It uses the value of x as an address, so we can see that. Or we could just go back to start and we could find that again, move EBX, so we could just put that number in directly. So I could put OX8049OD0, and we put that address in. And now this is data, so interpreting it as instructions, we're just going to get a bunch of weird instructions that are not what we want to look at, because it should not ever try to execute those bytes as instructions. It should be looking at them as data. So let's go to hexadecimal bytes first. And so here we see the 2A000000. That's the little endian for 0000002A. And that is the 42 that we put in there. Of course, we're looking at it as hexadecimal. If we want to go to the words view, now we see it with the flipped to with the little endian interpretation. So the 2A is now seen as the last byte instead of the first byte. And we see all the leading zeros. And if we want to look at that as decimal, we see it as for the 42 that it is. Okay. Now, but let's go back to the hexadecimal, and we see the FO that we put into Y in the next 4 bytes. All right. Now, one thing you don't see, because these are all identical, you're not going to see the little endian. You're not going to be able to tell that it's been reversed, but trust me, they did get reversed. Okay. So these 4 bytes here of these F0, F0, F0 are the reverse of when we look at it 1 byte at a time. F0, 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 but in reverse order. You just can't tell. All right, so and then let's see, what do we have in result? We put a 0 into result, so of course the next 4 bytes should be 0, 0, 0, 0, 0, 0, 0, 0, which they are. And what comes after is, for all practical purposes, garbage data. It's not anything we reserved for the use of our program, because we only reserved 12 bytes here for these variables. So, but the main thing I want you to get out of this right at the moment is, again, coming back to start in the memory view, and with the instructions interpretation, notice it remembers the interpretation that you used on the memory for each different address that you have a choice of here. That's kind of convenient. So switch back to start, and we're seeing that as instructions. And so once again, we see that the move EBX already has the numeric address. It does not have an X there. It has an actual number. All right. But let's look at something else. Let's look at the move ECX. Here, notice it threw in this D word interpretation to indicate the size of what is pointed to. So that tells us it wants to grab a 4-byte chunk. If we look at our original instruction, we said move into ECX, the thing pointed to by X. We did not actually ourselves have to put D word in here, because the ECX register implies that it's going to be D word, but for some reason, when KDebug interprets this word, it actually gives us the D word. It also tells us that we're using this number as a pointer, so it's actually saying use the thing pointed to at this address, okay, and move that into ECX. So here, we're actually moving X, the address X, into EBX. Here, we're moving the thing pointed to by X, the contents of the memory. So what is the contents of the memory? Well, then I have to go to look at the memory starting at X, and let's reinterpret that as hexadecimal. So that's these 4 bytes here, interpreted as a hexadecimal number. So that's 0000002A in little endian. So that's the number 42. So again, when we do this instruction, we're going to get that 42 copied into ECX. When we do this instruction, we're going to get that actual address of 80490DO. That's what's going to get copied into EBX. So let's actually see that in operation. Let's just set our breakpoint right here. Oh wait, we had this thing up here as well. Let's actually see this in action. So let's just step one at a time and take a look at what happens here first. So let's go look at the view from start, and let's actually do some steps. So step over, step over, step over. Now here we are on this command. We're about to move we're going to move what's stored in EAX to this memory location, and that's our result pointer, okay, our result address. So that's the address of the 4 bytes that we reserved here. So let's take it step by step. We're going to move. What are we going to move? Well, we look at the second parameter because that's the source. We're going to move the number in EAX. What's in EAX? What's in EAX right now is the 200. All right, remember we put 100 in, we put 100 in, we did a sum, and so we have the 200 there in EAX. We're going to move that 200 to the memory location given by this address. What is that memory location? Well, we need to see what result is, so if we look at the memory, we see that the address, this is the actual numerical value of result, 80490D8, and that address, if we start at X, or if we start here, these two are the same, ampersand X and this address are the same thing. So this is basically the start of our data section. Okay, so we have 4 bytes for that X is pointing to, 4 bytes that Y is pointing to. Wait a second. Why does Y? Oh, yeah, Y. That's right. Never mind. Okay, and 4 bytes that are currently zeros that result is pointing to. And here it does, on these addresses on the side, if there is a symbol that has that address for a value, notice it is showing us what that symbol is, which is kind of nice. So result is pointing to these 4 bytes. So what we should see is that the 200 goes into those 4 bytes. In fact, let's go ahead and change this view to words. So now we're looking, now it's showing us 4 words, 4 columns. So those same 4 bytes are right here on the first line. So this is 4 bytes for Y, 4 bytes for result. So we should see that go into there. So we're seeing this 200, or this hexadecimal C8. And again, we can look at these as hexadecimals. So 000000 C8. That is what we're going to move into the address pointed to by result. So let's actually do the step and see that happen. So the interesting stuff is going to happen in memory. So what we should see is that that C8 goes there. So let's do a step over. And there it is. C8 got moved into that memory. So the C8 from EAX, that's a decimal 200, got copied to this location in memory. Why was it that location? Because that's the numerical value of result, because result was defined here to be the address of a 4-byte word that was initialized as 0, and it's after this 4-byte word and after this 4-byte word, so it starts at offset 8 from the first byte of the data section in memory, and the data section starts right here, same as the X points to that first byte. So X is the address of the first byte here. This is 4 bytes, and these 4 bytes are what we just updated because we did the move from EAX into the memory location pointed to by result there. So now the rest of this is stuff that we've already done. So let's set a breakpoint up here to right here before these other commands go. And I'm just going to click run. Remember, if you just click run, that it continues the program until it hits the next breakpoint. So if I do that, it did all these instructions, got up to the next breakpoint. Now we are ready to move X into EBX. Now the bare x is the numerical value x. So x is this number. X is the address. Get that? Just pound that into your head over and over, okay? X, don't think of x the same way you think of variables in C programming. Think of it in the way you think of pointers in C programming. X is the address of where this 42 initial data is stored, okay? That is what X is. So, whoops, I didn't really mean to move that. So, this address right here, hexadecimal 80490D0, that is what X is, that number, all right? So, this command is just going to copy that number into EBX. So, let's watch that happen. Make sure it's absolutely clear. So watch EBX, click step over, and boom, EBX now has 080490D0. What does it not have? We did not put a 42 into EBX. We put the address into EBX. This address is where that 42 is stored, but it is not the 42 itself. Okay? Now, if you were ever having trouble with pointers, when you learned about pointers in C programming, hopefully this is starting to make pointers make sense, because this is really what a pointer is. A pointer is just an address. It tells you where something is in memory. All right, so basically EBX right now is kind of being used like a pointer, and that'll come up later. Now let's look at this next instruction. Now we're going to copy the contents that are pointed to by X into ECX. So this square bracket, this is actually a good example. Actually, I think I'll put this in the notes. Let's see, in NASM syntax and lots of other variations of the same basic Intel syntax assembly language. So this is a good way to think about it. So if you do have a kind of a good sense of how pointers work in C programming, putting square brackets around something in assembly is roughly the same thing as the asterisks on something in C. So if something is a pointer, an address, then, so let me put it this way in the notes, okay? So if you have something that is a pointer or an address, then you use square brackets around something in NASM assembly to actually do the same thing that you would use the asterisk for on a pointer in C. So remember, asterisk is dereferencing the pointer. So what I want you to recall from C, star some pointer dereferences the pointer, okay, or we can say that it refers to the contents pointed to, or the location pointed to, okay? So hopefully one of the ways I'm going about explaining this helps make it clear. Ultimately, trying different things, practicing, and making sure you have it straight in your head is ultimately what you have to do. But let's see how we're doing on time. This is probably long enough. We'll look at more examples soon. Let's just keep working through what I have here, though. So we are on this instruction, so we're about to move what x is pointing to into ECX, which means that that 42 right here, again, if we go to decimal and words, we see that it's a 42 in those 4 bytes right there. Okay, so we're going to copy that 42 into that register. Which register am I putting it in? I'm going to put it in register ECX. So let's highlight that and see that happen. So I'm going to do a step over, and there it is. Again, in hexadecimal, that's a 2A. Of course, if we go and look at that as decimal, then we see the 42 right there. So we just copied the 42 into ECX. Now I'm going to do something funky. I'm going to add 4 to EBX. That is straightforward. So we just have, here's EBX right here. We're just going to add 4 that. So we should just see a 4 in the last digit after this step. There we go. That's D4. Now let's come over to memory. Now remember, X was pointing to these 4 bytes, and Y should be pointing to these 4 bytes, which as a signed decimal is that negative 2 billion something, it looks like. But of course we can go here and we can look at it as an unsigned decimal, then it's a 4 billion something, and then we can look at it as hexadecimal, and we can see the F0, 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 which is what we actually put there, if you'll recall. That's what we initialized that memory to be. And so we're about to copy that into the next register. So we added 4 to EBX. So now EBX is that address. This number right here is the address of Y. It's the address of the first of these 4 bytes right here. In fact, we can put ampersand Y here, and then boom, this is Y. This address right here is Y. You can look at that address. You can come over here to the registers, and you can see, yep, same number there, same address here. This is the data stored in those 4 bytes. We can look at it as bytes view. And so it's a little endian, so we just reverse those bytes, but they're all identical, so we can't tell that they're reversed. But at any rate, now we are going to do this. We're going to do another move command, a copy command of the stuff pointed to by EBX. So EBX has this numeric address in it, and because I'm putting square brackets around it, that dereferences. So it's going to take the numbers stored there, the F0, 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 and copy that to EDX. So when we do that step, we should see that show up in register EDX right now. So let's do that step. Boom. And there we have copied the number from memory into EDX. And so now we're left with just the exit commands. So we've seen everything that I've created in this example in operation. Hopefully, this gives you a pretty strong idea of how dereferencing works. Now, what we haven't looked at, so this will be something we pick up with in the next video, is let me come back to the notes. So what we haven't looked at are indirect addressing where we have some kind of expression. All right, and there's basically kind of 2 ways we can do expressions. One is it can involve constants, addresses that are already known by the assembler or the linker, and so those expressions actually themselves just become constants. Or it can be an expression that involves registers, in which case the address itself is computed at runtime. And those are kind of interesting. So we'll be looking at those. In fact, let me break the notes down a little bit differently. So an address can be determined at build or link time by the assembler and or linker. So these all become constants or an address can be determined at runtime. And that's like our EBX, where the address was in a register, or it could be an expression involving registers. So this is, so it's these expression versions that we haven't looked at yet. Those are the ones that we still need to see examples of. But you've got the essence of the indirect addressing. We also haven't looked at a situation where we need to use the size keywords, so we'll pick up with some examples of that soon enough. But this is, now we're at a little over an hour, so I think this is a good stopping point here. So until the next video, signing out.